Okay, my name is Vladimir, and I'm Kaggle Master, and today I'll talk about solution that me and my partner just like tricks and tips and problems that we encountered to get like to the third place in this like deep learning competition. But before this, I would like to ask a couple of questions. Could you please raise hands, like all those of you who ever competed in any Kaggle competition and just like did at least one submission? So situation where you downloaded the data but didn't do submission don't count. You should be actual like submission, click, submit, leaderboard position, yeah? Wonderful. I mean, a lot. That's good. How many of you Kaggle Masters or Kaggle Grandmasters? One. Okay, sure, still good. Okay, how many of you participate in this like competition about satellite images? No one. One. Great. Okay, so for you it will be the most beneficial. Okay, let's start our talk. Let's start our competition. So first of all, like our team, two people, me and my buddy Sergey. So we started this competition independently. I live in San Francisco. He lives somewhere in Siberia. I will not be even able to show on the map like town where he lives. Okay, Dmitry can show this his town. But again, so it's like kind of international team in some sense, although we're both Russian. We have slightly different background. I'm more experienced in machine learning and deep learning in general. I work as senior data scientist at TrueAccord. It is a startup in San Francisco. And I do machine learning at work, like just for money, deploy models, prototype, deploy them, test, like at an everyday basis. Education-wise, I have PhD in physics at UC Davis, which is nearby, and again, I'm Kaggle Master, meaning like I got like to the top places a few times. Okay, my partner Sergey Mushinsky, he's less experienced in machine learning, although he's doing some kind of deep learning for his job, deep learning engineer. He is education bachelor in computer science, and as I mentioned, place where he lives, Angarsk, Siberia, Russia. In this sense, just like to emphasize this, like, you know, time zone difference and geography difference, it was very convenient and very good in a way that when I was like going to bed in the evening, just woke up, I was telling him ideas, he was checking them. I wake up in the morning, he just said, yeah, try this, okay, my time going to bed. So in this sense, it was very efficient, kind of like non-stop work. We didn't plan this initially. We met each other at the forum, discussing this problem, and then somewhere closer to the end, like probably like a month before the end, we decided to join and like to form a team, because I mean, together it's much better than like independently. Okay. So this is a mandatory slide that I typically give at any talk about machine learning and about deep learning. And when I was giving a talk here a couple months ago, 3 months ago, 4 months ago, I also had it. So point of this slide is there is some misunderstanding between people that do machine learning at work, they do for competitions, and they do this in university. Idea is that although it's all machine learning, it's really, really different. Things that you do in competitions, you will not typically see when you like machine learning at work. Things that you develop in academia, they will have like, they will not work. They may not work when you try them in competitions, at work in opposite way. And the reason for this is because although all of it is machine learning, when you optimize your models, you do this for different things. For example, in industry, you try something simple that works really well, fast, can fit into the memory. Let's say you develop something for a smartphone, it should fit into the memory, it should be very fast. Let's say you have a self-driving car, it should like process images in like almost how many, like 20, 40, 60 frames per second. And also it should be easy to support. At the end of the day, it's like only half of the deal when you like deploy some model in production. You need to monitor, check, manual review, you should be able to interpret what's happening to some sense. In the sense, industry, you typically don't use some kind of state-of-the-art, it's something simplified, but you're able to support, and that gives you like desired result. Academia is different. There is no way that you'll publish a paper and say, I did like the same as everyone else, that's why my paper is great. You need to publish something that is new, that addresses some point, maybe simplifies some new algorithm. So basically, novelty is the most important thing. There are some side effects in which people claim results that they don't deserve, but still, it's all about novelty. Competitions. Competitions stand aside in a way that it's totally normal to develop a problem that will run somewhere in the cloud for a couple of weeks. You will spend like $3,000 because like computer with 1 terabyte. And this like 3 months ago, Dmitry was like giving a talk here about his solution in which they dumped like $2,500 for Amazon to create some model that, and even using proper logistic regression within 5 minutes, you can get something similar. But to get this like better score, to get their first place, they just did this. Yeah, and of course you don't want to use it in production just because it's too complex to solve and something like this. But it's the most accurate model that people were able to create for that problem and that data set. So yeah, in this sense, problem model that I'll propose, this algorithm about deep learning that I'll talk about today, also I would not recommend deploy it to production, although after some tweaks and modifications, you can definitely like, try to get something out of it. So yeah, this is a mandatory slide that I'm like trying to emphasize that all these like 3 disciplines in machine learning, they are really, really different. And this intersection is as small as it looks at this picture, okay? And one more thing, so another point, main point of the slide, that if you do both, you do machine learning at work, you do computations, and maybe do something, some kind of novel research, you're great machine learning because you can cover all of these like 3 fields. Situation where you only do computations but nothing else, you just one-sided, same for academia, same for industry, and in this sense, like jumping from industry and develop papers like and publish them is kind of hard, but everyone can start competitions, and Kaggle is a good place to start. You just come, start, you don't know anyone, you don't know anything, you don't like know anyone, but there's community, people are helpful, and if you're just like thinking and considering and excited about machine learning and want to switch there or just start there, Kaggle is the place to go just to start some practicing, developing the skills, intuition, and etc., etc., etc. Okay? Okay, finally, to the problem. So what problem did we need to solve? What's this problem we needed to address and why? Okay, so we needed to create a model. We need to create a model that takes as an input satellite images in different spectrum with different resolution. On one side, on the input, yeah? So imagine that like you have Google Maps, Google Earth, and there's like some satellite images, yeah, and then you like click this button somewhere in your browser and it looks like maps, and it shows you that this is like green is road, brown is road, green is like trees, and something like this. So, and that's what like kind of literally we needed to do. We needed to have a model that takes satellite images on the input and create this mask, something that you see in Google Maps, as an output. Yeah? So we needed to divide, so all the satellite images for each of the pixels, we needed to predict if it belongs to one of the 10 classes. And they were buildings, man-made structures, road, dirty roads, trees, crops, waterways, underwater, and vehicles. Yeah? So standard image segmentation problem. Train set, 25 images. Test set, 32 images. 6 were part of the public leaderboard, public test set, and when during the competition, you knew prediction of your model on these 6 images. When competition is over, your final model, your final accuracy is evaluated on these 26 images in the private data set that you've never seen before. It looks like number of images is kind of small, because if you talk about ImageNet, like 2,000 pictures, 200,000 pictures for detection, for classification about 1.2 million, so like these numbers. And here it's only like 25, 32, 6, 26, something that's really small. And it may look that you can't apply deep learning here because it requires big amount of data, it has a lot of like free parameters, and it will not work. But trick is, so when you talk about some standard image satellite, when you talk about standard image segmentation problem, let's say you need to find in the picture where is human, where is dog, where is cat. You have some images, basically, let's say 600 but 1,000 pixels, and so there's not that much information there. Here, each satellite images was covering 1 square kilometer. So these 25 images in our train set, they were covering basically Mountain View, plus Palo Alto, plus probably something else, just its decent amount of area. Small number of images, but each of them contains a lot of information, and to train the model, we just like splitting them into like smaller parts. Yeah? Okay, so another difference. So like what this picture is about. Normally, when you talk about deep learning and you talk about images, you're talking about grayscale, just like intensity map, or you're talking about RGB images in which you have 3 channels, like red, green, and blue, and you're trying to do something about this. ImageNet and like most of the like deep learning competitions that you haven't done. Here, situation is different. The idea is when satellite is flying around the Earth, there is no reason for it to constrain images only to this like visual spectrum that like we people see. You can use infrared, you can have like higher wavelength or maybe lower wavelength, and this allows you to capture much richer set. So, and it was also the case here. So we, as a participants, were provided not just RGB images, we had RGB, we had slightly wider spectrum, which is named M band, and we had like a thing that is named A band, each even higher wavelength. As you can see in this image, RGB was part of the M, so it was included in this. Why did we need this redundant information? The trick is that all this like RGB M and A, they had different resolution. So RGB, it was something like 3600 by 3600 per one image. M, for the same area, exactly for the same like geography, it was something like 800 by 800 pixels. And A was something like 125 by 125. So as you can see, resolution is different and they carry different amount of information and they cover different parts of the spectrum. And again, question was, so typically when you work with deep learning and there are programs that you have at Kaggle right now, you have RGB, feed it to network, you're down, top, you're winner. And not really, but still kind of. And here it's again, it's not really that obvious. How will you feed to network all these things that just so many bands, so many ways to do it? Okay, so again, so this was kind of a description in terms of like text before, and realistically that's how it looked. So you have RGB at the left, you have something like P band, which is grayscale, panchromatic, high resolution image. Then you have lower resolution M band, and then at the right A band, and I hope you see that like, you know, resolution is dropping from left to right. Yeah? And at the end, you need to get something like this. And this is actually part of your training set. On the top is your input, on the bottom is your output. You need to be able to say which pixel in the image belongs to which of the classes. Yeah? Cool. You have a problem, you have like, you understand what's the input, what's the output, but like again, you can't improve something unless you know how to measure this. Metric for this problem was Jaccard index. What is Jaccard? So let's say you have like, you predicted that some area belonged to a car, yeah? And then the real car is slightly shifted with respect to this. And you need some numerical measure how accurate your prediction is. And for this, you do something like this. It's named Jaccard, or in many papers, it's used simple intersection over unit. So what's happening right now? You take each of the 10 classes, buildings, roads, dirty roads, cars, etc., etc. For each of them, you calculate this Jaccard index, meaning intersection over unit of your prediction and ground truth. And then you just take average of this, which is like written at the bottom. Okay? And during this competition, and this kind of important, we try to optimize with respect to this metric. If our metric would be a bit different, probably our solution would be like slightly deeper. Okay? Question?
Is the intersection of the polygons outlined around the output?
So question is, yes, so what exactly is this intersection of a unit? Our prediction should be for this problem, you need to predict, let's say you have this image 3600 by 3600, let's say just buildings, you predict for each pixel out of this like whatever, like 9 million. Does it predict to the building or not? Yeah. And also you have a mask, which is also this 3600 by 3600, for which you know who exactly belongs like which pixel. So this intersection over union is on this pixel level. Of course, you can like think about this is your drawing like rectangles about around the prediction and around ground. And realistically, it was the case. Of course, you just don't talk about each particular pixel, and then you just take average. But it was easy in some sense to think about this on the pixel level. Okay, so of course this is machine learning. Of course this is Kaggle. I don't remember, no, there were like couple Kaggle competitions in the last couple of years when there were no problems with the data. It's exception. Typically, it's just as usual. So, okay, what issues with the data? Issue number one. Due to the For this metric and for this type of the split, we were able to derive what is the class distribution, basically how many pixels, what percent of the pixels belongs to each class in all like 3 data sets: public, private, and public, private, and train set. Yeah? And this is what you see at the right. So top is train set, then public, and then like private data set. And as you can see, first of all, within each set, class distribution is different. When you read some machine learning textbook, or if you're taking some class at Coursera, people tell you, or maybe if you pass interview, like one of the questions that people like to discuss, if you have class imbalance, what do you do? Undersample, oversample, like extra weight, something like this. And they ask you, is like 1 to 100 is a class imbalance. And answer is, it depends on the data. Here it was much more entertaining. So if you can see at these plots, you see like crops, this like middle one, long one, it has this amount of pixels. But cars, bottom two classes, you don't see at all. And for example, in the train set, 1 pixel of cars corresponds to 60,000 pixels of crops. So it was like this. And also, you just can see like structures, buildings, so it's a really big class imbalance within each set. It's first thing. And second one, if you compare, length of these bars, if you want, for like top, pin, and bottom plots, you see that like there's something different. For example, buildings are more represented in the public, in the train set, rather than like in just in general, things like this. And what's the consequence of this? Consequence number 1, cross-validation will not work as well on this data set. Again, in every textbook, there are some words about it's very important cross-validation, and assuming the training test set that come from the same distribution, we can map it to maximum likelihood, etc., etc., etc. Great. This assumption doesn't hold. That's it. And this was, in some sense, a big problem. And if you can see, look at the leaderboard after competition is over. People were flying all over leaderboard plus minus like 100 places because they trained on the top part, validated on the middle, and reality is bottom. And it was like one of the problems how it works. Another thing, like typical models, they work decently well when class imbalance is not that bad. As let's say, if you have 1 to 100 and this amount of data, it's not really a big problem. But like 1 to 60,000, it's just like too much, especially if you have only 25 images in the training set. And this led to the consequence, so you see for each of these 10 classes, we created a separate model. No, even like this, we gave up on cars because like not enough of them. And we created one separate model for each of the 8 classes. And this made validation more stable because, I mean, we didn't have this issue that crops were pretty bad and they overcome buildings and things like this. So yeah, it was like separate model for each class. Question?
How did you get the site into the private set?
Okay, how did we decide like what is the distribution in the private set? We knew it after competition was over. So yeah, there was no way to know like which images are public, which are private, and what's happening. But when competition was over, we were able to find this bottom picture. So yeah, there was no way to know it in the beginning. But even difference in the train and public is big enough to decide that different models will better. No, of course we tried like to do one model to predict all at a time, and it can give you to the top 10%, but not higher. And if you want higher, this picture was helpful for us to realize that you just like need separate models. Another thing, like as I said, like 25 images is not enough, but it's still 25 images. It's only 25 square kilometers. And let's say if you have not 25 but 250, maybe the story will be different, different models, different approaches, because I mean more data, more patterns you can like extract, and you can even like use simpler models to get better performance. Data is very diverse. Out of these 25 images, we have towns, jungles, farms, and they're really different. So you can have like most of them are farms, and as you can see on this, like how much crops do you have, but still, data is pretty diverse. There are mistakes in labeling. I'll show like a couple pictures later when some cars were marked as the trash cans and trash cans are marked as cars. There were some roads that go like to the forest and the end, and then like when like a few hundred meters later they start and things like this, but more try to separate, so there were issues with labeling. Big class imbalance and dimension in different distribution train, public and private set. Okay, issue with the data. Question?
So what would happen if you did well on the private test but did poorly on the public test?
If you do great on the private test, this is amazing because that's how your model is evaluated. Question is different. Let's say you do well on the public set, but you don't do well at the private. Such is life. You get that place of the opposite.
So say you did badly on the public test, but you did well on the private test.
It's very unlikely that you participate in the competition and on purpose you try choosing something that performs bad at the public.
Well, I'm just thinking, what if you use the public test data as training data? And
you don't have labels for your public data, so you don't know. You have only, so that's the point. You have this definition, train and test. For training, you have labels. For test, you do not. And test is split into parts to prevent overfitting to the data. Okay, so again, what's happening here? So, and it's about, so initially we're surprised, what's happening there? What's the point? And like, how does it happen? It's the same car. On the left, on the right, it's exactly the same car. And stories like this. So when satellite is flying over the Earth and it's taking images, for whatever reason, this type of the satellite, it was taking one in some channels were taking a couple seconds before other channels. So if object is moving fast, you may happen at the same images in one channel, like something in one position, and second later, it's like somewhere. And because we need to do pixel-wise prediction, where do I need to predict it? Because I mean, I don't understand it with my eyes, and model will be even more confused. Another thing, maybe it's not even clear at the bottom, but you see there are some cars marked at the top, and there's like some trash cans or dirbys or something like this at the bottom. So overall, these issues with the data, these things with cars, made us decide that we will address things with cars later on, and we never had time to do this. If we invested some time, maybe we finished second, because like our difference between second and third place was pretty small, but such is life. I mean, we did not, and competition is over, so there's nothing to discuss. Yeah? Okay, let's talk about some artifact here. Let's come back here. As you can see about waterway and standing water, there's like really small amount of data in the train set. And there's a decent amount of this in the test set. We knew that it's more of this in the test set just because you can, like, you don't have labels, but you can open your images and look at them with your eyes, and you see like white rivers. There was some region in Nigeria, and so small amount of data in the train set and large in this made us decide that probably made us ask, what other ways do we have to find water? Because realistically, this deep learning explosion in 2012, interest to it, it was just only recently. And people analyzed some satellite images, and they were trying to do some prediction on this, some analysis for like how many, like 20 years or something like this. Yeah? And we looked at the literature, and apparently there are like a number of ways to deal with the data in unsupervised regime, purely on the pixel like level values. And this works really well, especially because you're able to use infrared channels. Trick is, as you know, like, let's say vegetation. It is extracting energy from the sunlight, so some sensitive in some sense to this, and it's combining different channels. You can combine it in such a way that pixel values will be very conscious, let's say, for vegetation. Vegetation was working more or less well, but this picture is about water. As you can see on the left, some satellite image, and on the right, yellow, which is pretty bright. You basically can see like water on the right, and there's like some also like dots that correspond to the buildings. Yeah? And this is purely pixel values. So what's happening? There's a equation at the bottom. It's named index NDVI, and if you just like take on the pixel level green channel, subtract infrared, and then divide by this, so that's what you get at the right. And you don't really need machine learning, only something like complex to describe it. Like logistic regression or something like this will work pretty well. We didn't even do this. So to find water for this problem, and for running water, we got like 96% accuracy, and for standing water, about 60% accuracy. We did this. You do this and say that everything is above some threshold is water. That's it. You're done. And this was our probably the most, like, the best chance. So what I'm trying to say here, there is no need to use some complex models or something like this. Sometimes, but not always. Unsupervised simple approaches may work well, especially if you take advantage of some physical properties and some nature of the problem. But again, if you had like much more data, we probably wouldn't do it. Just like deep learning would pick it up like even better. But again, in some sense, we were enforced to use this unsupervised approach, and we were happy that we found it. And it worked really well, but it's just artifact of the fact that we didn't have enough data. Yeah? Okay, so as I said above, we use this like difference of near infrared and green and bottom like this sum to find this water, but what about other channels? You have A band that has 8 channels, we have some other infrared, we have like green, blue, etc., etc. And then if you look at the literature, people created a number of papers and they claim state of the art, and they published to the conferences. And what they literally did, they took different arithmetic combinations of all these different channels and got slightly different pictures. And for example, I don't remember what it's exactly on the like bottom left, but like water is pretty bright. Something like top right, like this vegetation is also pretty bright. So we like again created this like simple indices and like water index, vegetation index, some other vegetation index, some chlorophyll, whatever it is. So basically we also wrote these things and they were used as an extra input to our neural networks. Yeah. Okay, so again, we had 10 classes in the beginning, cars we drop up, we dropped 8 left. For 2 of them, for standing water and for running water, we use this index and DVI. 6 left, meaning buildings, man-made structure, 2 types of the roads, crops and trees. And for each of them, we trained a network. Network architecture I show a bit later, but general pipeline looked like this. You took RGB, PM band, and all these 4 indices, you stuck them together as a huge sandwich. So each picture that we fed into our network had, I believe, 16 different channels. So not 3 as usual, but like 16. And then you get like some big chunk. Yeah? Then there is no way that you will be able to train network on these huge input images that had 9 million pixel values in each layer. So instead, what did we do? We were cropping small patches out of this size 112 by 112. Combining them into budgets like size 128, applied augmentations, flips, rotations, and then we're feeding this to network, and that's what we get at the right. Something like this mask. Yeah?
Question.
Yes, question?
How did you basically fix the M-band and P-band together? Because they are...
Okay, question is, so as I mentioned at the beginning, M-band has resolution of these like big images, let's say 800 by 800. And RGB has 3600 by 3600, like how you combine them together. There are different ways to do this, and team that was on the second place, they had like very interesting solution, and like said we didn't use it, although performance is the same, but we just used brute force. We stretched M, rescaled it, so that it would match like this like RGB size and stuck them together.
But they may not be
They should be aligned. Okay, so about images being aligned, technically they should be aligned. First of all, because RGB was recreated from the M images. Like this satellite didn't collect RGB in the first place. So people used M and P to create RGB. So yeah, this is first of all, and they correspond to the same area. Realistically, they still didn't match, and there were some shifts like here and there for a few pixels, and we tried to do some rotations and stretches and shifts to merge M and RGB so that they match a bit better, but there was no influence, so we gave up at some place. Yeah? Question? About loss function, I'll talk later because it was also important here. Yeah? About network architecture, loss function, I'll talk a bit later. Yeah? So like it's just like high level overview. We created this, like we combined RGB, PM, and 4 indices, stuck them together, cropped subsets, created batches, fed to the network, trained it, and got something for the output, and we repeat this 6 times for different channels. Yeah. Okay. Question?
Yeah,
right. Like what? So question is like, what preprocessing did we apply to our tasks? We didn't do any preprocessing. Reason for this is that if you use something that is decently simple, network would catch this like in any way. You may think about this preprocessing as we added this extra 4 indices because I mean that's just simple, but we thought about this as extra domain knowledge. But realistically, we didn't do anything, just cropped, because networks, they work pretty well. And in general, if you work with convolutional neural networks, there's some papers, and it's also like in the clear math, You can apply networks to images, or maybe to Fourier transform of them, or you can apply to RGB or HSU or some other different things. You'll get exactly the same or very close to this, just because I mean network capture these interactions in the first channels, and then later on it doesn't really matter. Yeah? So yeah, we didn't do any preprocessing. Okay, so network architecture and loss function. So about network architecture, I believe all or nearly all image segmentation networks these days, they are based on the idea of this autoencoder. First you encode something, meaning you collapse. You find some kind of different representation that loses some small features, and then you like decode it to get back to the original close to this image size, and that's how like all segmentation works. And for example, SegNet is like a great example of this. Later on, at some point, there is some, I believe in 2015, for some medic images, authors introduced network, the architecture that they use the name QNet, and it's basically the same as SegNet, so it's the same decoder and then encoder, and they all the added skip connections. This person, author, was invited to DeepMind to do research, and he works there right now, I believe. And so network is pretty like good and accurate and pretty simple. Later on, actually, Facebook reinvented this and named it Sharp Mask. And overall, yeah. So there's like some other architectures you can do it more complex, more layers, more skip connections, some other magic. Yeah. Why did we use it? Because in the August of the last year, there was image segmentation competition at Kaggle, UltraNerve segmentation, something again about medical images, and I finished the attempt, and that's how I got my Kaggle Master. And basically, all top, I believe, first 200 places, they used QNet with some modifications. It was so much better than everything else. And we tried different network architectures. But basically, it was our baseline and worked really well. We tried different, but still, for this problem, it worked well. Main architecture is kind of simple, small number of parameters, so you don't need crazy amount of data. It converges pretty fast. So yeah, worked really well. So this is about network architecture. About loss function. Typically, when you do image segmentation, you use per pixel, use something like softmax per pixel with categorical cross entropy. You use background as some extra class, and then you take average of them, and that's what you do for image segmentation. The reason why you use softmax as an output and categorical cross entropy, because your classes are typically mutually exclusive in image segmentation. One pixel belongs either to Apple or a person or road or something like this. Here it wasn't the case. I didn't mention it before, but for this program, there was like decent amount of cases when the same pixel belongs to two or maybe three classes. For example, car that is like going on the road, pixel belonging to the car, also belonging to the car and also to the road. And maybe there was some like tree hanging over it, there was pixel from the tree, I don't know. So for this program, classes were not mutually exclusive. And typically for these cases, what you use sigmoid function as an output and binary entropy per pixel, and they take average. And this will give you decent results, and people within top 10 places, probably 20, they use it. But you can always go deeper. And trick is, I didn't see this in literature right now, I'm preparing a paper about this, and we'll probably talk about this more. Idea is when you work on some machine learning problem, you have loss functions. So things that you try to optimize, to minimize, to get good solution. And there is evaluation function, something that you need to evaluate some more. And they're not necessarily the same. Because let's say you can have some F1 metric and for some binary classification, and your loss function will define the cross entropy, and then you try to match them, threshold, there's some magic like there. Yeah? And so here, what did we have? Our evaluation metric is Jaccard, meaning intersection over union. And our loss function, we could use this binary cross entropy. Yeah? So there's some mismatch in a way. In competitions, people try this idea, and it worked pretty well when you try to make your loss function as close as possible to your evaluation function. So basically, you make your models to optimize directly for what you want to see as your result. Yeah? So what did we do here? You can't use Jaccard directly, because Jaccard works on binary values. You need something like zeros and ones for your ground truth, and you have it, and you also need zeros and ones for your prediction. But your prediction with sigmoid outputs, its probability from 0 to 1, and so what do you do? So trick is, and again, this comes initially from this ultrasound nerve segmentation, when you modify, when you create some generalization of Jaccard in a way that it will be able to find an intersection over union of probabilities of something belonging to some class and ground truth values. So you extrapolate, you generalize it from integers to like floats, yeah? And that's what is written here, this equation at the bottom. So when y true and y pred, they're like zeros and ones, it's exactly Jaccard. But if y pred is something from 0 to 1, you still can use this equation. It will just do it in a different way. And what did we do? We take binary cross entropy, we get this Jaccard approximation, and we asked our network directly to optimize for this value. And we believe that it improved network accuracy. As I've said, it's not that much because, like, in the perfect world, when everything is great, it should be like 0 in both cases, but for our data, it showed that with this loss function, it converges faster and converges to better values, and overall, it's a good idea to do it in this way. Yeah?
So if you have a car on the road, what will be the value of y true for that pixel?
Okay, so if you have a car on the road, as you can see, there is like at the bottom, like something like this, 1 over n. So what's happening? Your loss function is calculated in this way. You calculate Jaccard independently for car, for road, for trees, for crops, and then you take average. Here is happening in the same way. If some pixel belongs like to the car and to the road, in your loss function you have separate term for car and separate term for like road, and then you take average of them, and that's it. So in this sense, this like equation is agnostic to like they belong to the same class or different. In this sense, yeah? Okay. So we trained our network, we got this picture, and it looks to some extent, in some sense, nice. You see some roads, you see some like trees, you see some crops, this light green, but this square structure is kind of shady. Why is it happening in this way? As I've said in the beginning, like, you know, we need to do predictions on the images of the size like 3600 by 3600. Our network is trained on the patches, meaning it takes input and produces an output of the size 112 by 112. Yeah? And what do you do? Like in the prediction time, you just like take your big image, divide it into like small tiles, predict them independently, and then like combine them back together, and you get something like this. I mean, it's better than random, but I definitely don't like this like clear square structure. So why is it happening? We just did an experiment. So we looked at accuracy of our prediction as a function of the distance from the center of our network. Our network was producing patches 112 by 112, and you can measure basically how accurate your predictions when you go away from the center, because you would expect, because there's a lot of zero padding in the middle of this your encoder-decoder structure, that accuracy will decay to the sides, and that's what we basically got. So on the right, you can see that when you get really to the edges, like your error is jumping up, and that's the main reason that you get like the square structure in the sides, because centers are fine, and on the sides, predictions are bad. So what did we do? We added cropping to the layer that was cropping our predictions of the network. So we modified network structure in a way that at the input, it takes 112 by 112, and at the output, it gives you only the central part, 80 by 80 pixels, just based on this like something. And this was our way to avoid like boundary effects. Question?
Why don't you just overlap your original tile, and then you just add the scaling, so you like smooth integration rather than just by you'll get some edge effects anyway.
This is true. You still get some side effects anyway, and we're thinking about doing this latest, about doing this, but basically answer is we were lazy to implement this, and we had another trick to like address this issue in some other way. I totally agree with you that this like sharp cut adds still some, it decreases boundary effects in this way, but you still have them, but we found a better solution to address this issue without extra work from our side. Yeah? So what's happening here? So on the left, as I mentioned, you take this like picture that you need to do, and you divide this into tiny tiles, and you do it in a way that they're slightly overlapping, because like as an output, you're combining 80 by 80, and you're like taking 112 by 112 as an input. And you need like integer number of tiles, and what do? You just like add some zero padding, you add some zeros on the sides to make it, let's say, not 3600 by 3600, but like in a way that integer number of tiles. And we did this prediction, and then I looked with my eyes at these images, and I don't like it. So what's happening? At the area where you added the zero padding, I got like buildings predicted all over the edge, like 16 pixels of buildings predicted all over perimeter. I believe this happened because network was looking for some kind of sharp edges, and it was interpreting this as the buildings, and this looks pretty sharp to it, and then just like sure, it's like all of the building. So how do we address this issue? Again, in this like it's kind of like well-known issue, and in this original paper about UNet, guys were struggling with the same, and their problems was much sharper because they had like also even smaller number of images in their set, and you just like basically add zero padding. What's happening in this sense? You add zero padding, meaning reflection to this like black region, and this allows you to keep distribution of your pixel values within the image the same. And after adding this and doing prediction and cutting this, it was totally fine. No, this like boundary, like prediction, like building artifacts. So in this sense, this tricked really well. Again, in terms of accuracy, it doesn't add you this much. So right now, we're already fighting for like some third digit up to the decimal point. We're already in the top 5 places, and we're already good. But you just want to get higher, and people are tired. So I'm emphasizing it, so like from production quality perspective, when you're trying to do the support, you would not do this because it's extra work, extra pain. You need to like figure out that you didn't mess up with these indices. And in terms of accuracy of your prediction, it doesn't give you that much. Basically almost nothing, but in competitive environment, when people fight for like 5th digit up to the decimal point, they can do something. Yeah? Okay, test time augmentation. Often when people work with images, you want to expand your train set. And how do you do this? Because from physical perspective, you know that let's say if you have a cat, then you like, and you need to distinguish cats and dogs, and you like flip them or rotate to make a stretch a bit, it's still a cat, it's still a dog, but it allows you to make the train set bigger, and this allows you to train more complex models, or if you like your model is still like same size, you can think about this as regularization. Yeah? And this is about train time augmentation. As I mentioned, we're doing this in a way that we're like flipping, rotating, and by 90 degrees, and use other transformation from the like group before. But you again can do the same trick at the test time. In competition in ImageNet, they tend to name it, let's say, 10-time crop prediction or something like this. So what's happening? Let's say you have some image and you need to predict if it's a dog or cat. You crop 10 different regions out of this, and then take average of them. And it's much more accurate in terms of prediction if you do this for one crop. Yeah? And we kind of like same reason here. So what's happening? Let's say, again, I was kind of sick of the satellite images when I prepared this presentation, so I just like added some killer from Jungle Books. Okay. If you have some image, you can do it like you can do prediction like in the vertical or rotated or maybe some other rotation. So for each of these pipelines, you take image, you expand this to this region to like be able to fit integer number of tiles. Then you use reflection pattern to like expand image there. And I want to emphasize that like on the bottom of the top, it's done in slightly different way. Yeah, because like you can see. Then you divide this, then you do prediction. You can see here, I tried to make it, but guys on the almost to the right a bit of blurry, and on the right when you combine them using geometric mean, and of course we use geometric mean because we talk about probabilities, you get something that's a bit sharper. Yeah? And this allows you to add a bit more to your prediction quality. Again, I don't think it's the right idea to use in production because you get a bit in terms of accuracy, but your prediction time increases twice. And we used it for 4 different orientations. So, and this means that our prediction was taking decent amount of time. Yeah. Okay, actually that's it. That's like this, like just few ideas in network that allowed us to finish that. And here I want to show. So this on the right is satellite image, and on the left is our prediction. Sure, it's not the best. Sure, there are mistakes, but overall, I was like really impressed by what's happening. Road is pretty clear. Yeah, there are some breaks, and you can use morphological transformation to fill them. Road, I mean, dirty roads, buildings, some ponds, cars. Yeah, we didn't predict cars, so it's not them. No cars here, but still look pretty well. Looks pretty well, yeah. Okay, so again, summary to emphasize and summarize what was happening here. We were taking satellite images as an input in different resolution corresponding to different spectral bands. And as an output, we needed to predict masks. We needed to predict for each pixel, does it belong to each of the 10 classes? Classes were not mutually exclusive. As I said, you can have 3 overhanging over road, building, or something like this. Yeah? What did we do? We gave up cars. For water, for 2 water classes, we used unsupervised approach, meaning indices, NDWI. Something like, no, I will not say what it is. For other 6 classes, we used UNET. This network that performed really well in the previous image segmentation program, and that's what we believe it's pretty good, like as a baseline for any image segmentation approach. As an input, we used 4 indices, CCGI and DBI, EVI, and something else. We combined it with stretched M band, with P band, and RGB. And we also used distributed reflections at the sides, and we used test time angle augmentation with geometric mean at the end to combine them together. In terms of hardware, because it's also like pretty popular question, like how much hardware do you need? Like if I have a laptop, if it's enough. And answer is it depends on the competition. For example, right now there are a couple of competitions at Kaggle that probably laptop is good enough to create something decent. But this is deep learning problem. You are creating models that have millions of free parameters, and you're processing images, and you basically need some GPU. There is no way that you'll be able to get to the top without GPU for deep learning. Although for this problem, there was one guy, again, some Russian guy who studies in some university in Texas. He used XGBoost to predict pixel values for this problem, and you know he got into the top 10%. So I mean, just pure pixel values, no contextual information, these other things that neural networks are good at, but still whatever works. I mean, he was brave enough to try, and he got a good result without GPUs or anything like this. Yeah. So yeah, I believe I didn't look at his solution. I can ask him, but realistically, I believe he took. But you see, it's not just like RGB where you have 3 values. You have M band, A, and something like this. Maybe he also took nearest neighbors to make a feature set feature, but still something like this. Basically, XGBoost. Let's just use it. Yeah. Okay. So that's why in terms of hardware, I use my desktop, and I have Core i7 at home, 32 GB RAM, and 32 GB RAM. It's decently enough to work on nearly any deployment problem because I mean you create batches on the running time, so you don't really need a lot of GPU. Although if I had a workstation 128, I wouldn't complain. Yeah? Okay, in terms of GPU, I have Titan X Pascal. It's probably the top GPU this day on the market, but comparable in performance and twice cheaper is GTX 1080 Ti. And if someone is thinking which one to buy, probably get GTX 1080 Ti. It has a bit smaller amount of memory, similar performance, so good choice. Sergey, he has a bit more powerful CPU, although for this problem you don't need this. He has an enormous amount of RAM. Again, not necessary, but you still can use it. And he was like GTX 1080. There was, performance-wise, it wasn't really a bottleneck, but it has less memory, and it enforced him to use smaller batches and to write some other modifications to use like network speed. Basically, to be able to fit everything into the RAM of your GPU, he needed to do some extra tricks and hacks and things like this. Yeah? But still, it was enough for him to get to the top. And again, this is in Kaggle competition situation where we are excited about this problem, let's form a team and we'll perform well. It just doesn't work. It may work for some other tasks, maybe like in academia, maybe in industry, but in competitions, teams are typically worked in a way that you are at a similar place at the leaderboard. So, and when people somewhere closer to the top and they just know that they understand the problem, they have some ideas, they can combine their solution and they can go higher. Yeah, and this is the most realistic, most efficient way. I mean, of course, I mean, if you work on some competitions and you're teaming up with some person, if you work with some other competitions, later on you already know that you're both cool guys and you can discuss teaming up in the beginning. But if it's not the case, teaming up is happening somewhere close to the end with people that have similar performance at the leaderboard, the public leaderboard. And so Sergey, with his GPU, he was very close. Like I was a bit higher. like probably like 20th, he was 25th or something like this, and then we teamed up and we go pretty fast with the top 10 and stay there. Yeah. Okay, last slide. So probably like some of you, like you try deep learning, have experience, like they were really like smart with questions right now. But again, next question, so what? I'm excited about deep learning. I like to talk, so what? I want to try. What should I do? And the fastest way to be able to use some kind of deep learning, I mean, of course, I'm assuming you watch some like online class or maybe like some tutorial about TensorFlow or something, and then you just want to try it because it's not enough. Like, I mean, if you pass some tutorial, it doesn't mean that you just grasp it in some decent way. And the best way to do it, you pick some competition, even if you don't know what's happening, you just don't understand the problem, but there's another month to go, 2 months to go, let's just do it. And within this time, you'll become an expert in this to some extent. Yeah? And this slide points you out that 4 deep learning competition that just I have in my mind. I would love to participate in all of them, but like there is expectations versus reality, and so probably I'll pick some 2 of them, or maybe we'll see. So first one, it's about its classification problem, predicting some kind of like cancer thing there, so it's classification. Second one, there's some satellite images, again, satellite images became popular these days. Satellite images, some sea lines, enormous amount of data. And you need to count like number of sea lines per image, also pretty cool, nice images, interesting problem. So you don't need to figure out where the sea lines are exactly, but you just like need to say, on this image, 25 adult males, 12 females, and something like this, yeah? So also pretty interesting problem, and I'm looking at this right now. Third one, and of course, yeah, prize money. So first, second, and fourth, they're hosted at Kaggle, and Kaggle typically like, likes to give money to the viewers. So if you like want to get some free cash, this is the way to go, especially first one I like it the most. Yeah? Okay, third one. There's no money there, but it's ImageNet. ImageNet, all this explosion about convolutional neural networks, it started after like Alex Krzyzewski, yeah? Basically his great result when he crushed all competitors in 2012 using convolutional neural networks. And after this, like they became popular, and even this discussion right now we probably have because of his results at that time. Yeah, and it was happening with the ImageNet, and after this, ImageNet is well recognized in the academic community, workshop conferences, enormous amount of data. As I mentioned before, like situations where Kaggle provides you problem with the clean data, it's extreme exception. ImageNet, pretty clean data, a lot of this, no problem with validation. Just do it and go with it, and it's pretty interesting. Probably that's what I will focus on. And fourth one, it's again satellite images, but it's again classification. Amazon forest, you need to classify that this has river, this doesn't have river, or I don't know, I didn't look at this. Fourth looks the most straightforward, so if you pass tutorial about MNIST, fourth is the next step. Because I mean, it's slightly harder, but not conceptual, not fundamental. Yeah? So again, I'm recommending you, like, for those of you who are excited about deep learning, who want to try, to fail initially and then to succeed and go over the top, but again, to have a lot of fun, these are probably like the good places to start. Yeah? Thank you. There are some questions on the way, but again, if you have something to ask right now, yeah? First place okay, so what did first place winner did? This guy took this competition very seriously. For me, you know, I have work, I do like rock climbing, I like going dancing in the weekends, and sometimes I like walking around San Francisco, maybe taking pictures, having like drinks with beers, and with like friends, you know. There's life, you know. So like for me, competition, so how do I like typically work on competitions? So there's a problem. Yeah, you invest some time, maybe a couple evenings, maybe a weekend, I create pipeline. And after this, when pipeline is ready and training model takes some time, you just like start, you have some idea, you implement this pipeline is already ready, takes data, training model, prediction, maybe consolidation, something like this, and you're doing your stuff and it's happening at night. Or maybe go to work, check another idea, and that's why I'm even like with the fact that I hope I have life, I'm able to like do some kind of machine learning competition because you invest in the pipeline and then like pipeline is spinning on your computer and you're doing your own stuff. Yeah? This guy, I don't know. basically in this competition, it was possible to do 180 submission maximum. He did 180 submission, exactly. So he was doing them every day. And he got to the top pretty close in the beginning, and like, I mean, he stayed there for all this time. Later on, when he shared his solution, and if you're interested, you can look at the, basically he and our team, we published the description of our solution as a blog post at Kaggle blog, no free hunch, and he published his solution, and we published his solution. I mean, he also used UNet, he didn't use like some of our tricks, but he used some of his tricks. He predicted cars. He said that he invested like half time or something like this on cars, and this was probably the difference between us and him. You cannot say that his solution is 100% better. For example, like, I mean, later on I created some table in which top 5 teams share their predictions per class. Overall performance is measured in total, but you can look per class. And per class you can see the different like teams with their approaches to perform like better. For a couple classes, our predictions are the best. For like 4 classes, his are the best. So I mean, it depends. So what did he do? So as I mentioned, we used one network to predict. But again, you see, we're using patches 112 by 112. Well, you can do it in a different way. Create one network and train it to 112 by 112, and another one, let's say, to 56 by 256. And then you just like take average of them, because they address this data in a slightly different way, more receptive field, like less receptive field, focus on different things. And he created a number of these different models and took average of them. So conceptually, the solution is similar to ours, but more complex, used in some in a more aggressive way. Yeah? Next question?
How is judging done? It seems like it could be kind of subjective.
What do you mean subjective? So, okay, so again, about judging, you have your data. Organizers, they have, whatever, like 32 plus 26, whatever images, and for each of them, they have input, they have satellite images, and they have per pixel values where this pixel belongs. Then they split this into training set, and for these 25 images in the training set, that's what like participants are given. So we have as our training data 25 images for each pixels. We have satellite images, and we know where it belongs. Yeah? Then we also have test set for which we do not know answers, but organizers do know. And basically, of course, like after we do prediction, they can like numerically calculate like our prediction versus ground truth, and then you get some numerical value, and it's not subjective in this way. It's just a number.
So it's like an aggregation. They basically do a count of aggregation, and it has the highest number of links.
Yeah, in some sense, yes. Question?
Can you talk about how you became a physicist and then how you became machine learning?
Okay, how I became a physicist. It was on a date. It was in school. I was thinking going to archaeology because I'm excited about history. I'm more excited about psychology and like how people think, interact, and things like this. But I met this, I wouldn't say woman, was in school, so girl, and she was crazy into physics, and she was talking so passionately about stars and travel to stars. She didn't know physics that well, but she was just passionate and excited. And who knows, either I was so much into her, or she talks to like so passionate. I started considering physics, and because yeah, I was always like good in math. I mean, it wasn't really like some like huge change in me. I got more and more excited, and then after university after school ended, and I need to decide where to go. Like most of my friends, they went to computer science, just like computer science, like just boring. It's not even science. It's physics. Physics is like there's like physics and there's computer science. And so yeah, I went to physics, and I don't like and then because in some sense, you see, motivation physics explains you how to work, how life works in some sense. Because I mean, computers can't go artificial intelligence here or there. Laws of physics are laws of physics. I mean, and I stayed there, and I got my master's in high energy theoretical physics in Russia. Then I came here for grad school, and I was doing condensed metaphysics. And I love physics. I like science in general. And overall, I would be happy to switch, like from more data science position to like more like research position. And if I have time and money to do this, maybe I'll take sabbatical, try to apply machine learning models and some ideas like in physics and math and something else. But I mean, it's for this I need to give up my job and find some more research position, etc., etc., etc. Okay, how I got to Kaggle? Close to the end of like school, you're graduating soon, you get your PhD soon, and the question is like, so what? What's next? So typically what people do after this, they like say, most of the people say, I mean, academia is for dummies, like you want to be real people, let's have a job, let's like be an office plankton, work from morning till evening and be happy. Other people stay in academia and they work for like, as a postdoc and base pay, I believe, for postdocs, and you're world expert in your area, it's about 40,000 per year, and you're getting like even worse than in grad school and things like this. And you look at all this perspective, they don't look cool. And this was really bothering me. I didn't want to go to software engineering because like I'm creating some another pipeline, distributed computing, or maybe some web forms or like databases. Doesn't really sound exciting to me. But somewhere close to the end, about 6 months close to the end, when my buddy, he was also studying in our department, he stopped by and I gave him a drinking beer and maybe his passionate talk or something like this. He was no, it wasn't the case. He was talking about data science. He was excited. He was telling about some office supplies, aggregation within database. And just like, man, I was like doing quantum mechanics like yesterday. The office supplies don't look exciting. But he mentioned salary, and I mean, I don't care about money that much, but difference was pretty big. I mean, and then later on, some other of my friends stopped by and he talked about deep learning progress, somewhat more exciting. And this made me think that it's probably time to move from academia, where our perspectives are kind of shady in a way that it's not clear what really like you can do, and you don't get that much knowledge. And I started thinking about switching from academia to data science. Cool, I decided to do 6 months till graduation. I'm working my thesis. And after this, I need to finish and start applying for jobs. By itself, it's a hard question, like, hard profits applying for jobs, but also you need to have some knowledge. And I go into data science, and you have no clue what data science is. You open internet and they're like, we data science here and there, and just like, give me some structure, at least like where to start reading. So I started like watching some online classes at Coursera because at least they have what data science and they promised me to give me some structure about what's happening there. And then I watched and saw in one of the classes there were some discussions about machine learning, and they mentioned Kaggle. And it looked like a great place to practice your skills. It didn't look obvious to me that it's a great place to like learn some machine learning theory. But it became really obvious to me, especially after I tried, that if you try machine learning, and then you just stuck, and then like, so what, you want to get better as leaderboard, it's not even about money, but you just want to be better. And when you're in the bottom 10%, there's like solid proof that you're not as good as you thought about yourself. And then you start watching more online classes, you start reading papers, you start asking questions, you start reading form, and slowly, piece by piece, you go up. And it looked to me, and I enjoyed it the most, and it looked to me as a way how within 6 months to like get some machine learning knowledge. It's still one side, it still doesn't help you how to, just doesn't explain how to deploy your model in production, it doesn't answer a lot of questions, but it's better than nothing, it's still. Yeah, that's how I started, and I mean, initially I participated in all competitions, and now only in those in which I believe I get the most knowledge. Yeah? Question? By the way, question is, what happened to this girl who, like, twisted my life in this interesting way that I'm here, like, talking to you about this, like, telling you these fairy tales? She actually like, stopped being excited about physics and went to some like international relationship or some other shitty degree. Psychology, like who knows? I did like, somehow I lost contact with her like pretty soon after this school. Okay, next question?
So what was the difference when like working with you and the other guy? How to combine?
So okay. Question is like our third place versus first place over this like guy. I mean, realistically, it wasn't even combining modes. So at the end, we had different modes. They were both. So how could we combine our modes? Of course, we can take like couple modes from me, couple modes from him on the pixel basis, just like comparing using majority vote to pick one that works the best. Or we can take predictions of our modes, like and probabilities, and combine them using geometric mean. And if we join somewhere 1 week before the end, that would probably what would happen. And team, also some Russian team on the 5th place, that's what they did. They used this majority vote of their predictions. But we merged somewhere 2 weeks or maybe 3 weeks, a month, I don't remember, before the end. And things that we tried at that time and ways that we tried at that time, they were not part of this final solution. It was slightly different at the time. And so at least we didn't merge our models. We had one set of models. We were just like, our team worked not all the way to different sets of models and we merged them, and this is the standard way within a competition. we just checked our ideas and we're iterating on the 24-hour basis. And yeah, I'm saying 24 because I remember at the end of the competition, because normally in the beginning, you know, your model trains for 5 hours, just don't care. I sleep 8, you like, you know, start this in the evening and like check in the morning, that's good. But like at the end, there's 3 hours, can't waste that. And I was putting alarm at night and checking restarting models, visualizing and things like this. So yeah, it was kind of like 24. Part from me, part from Sergey, and our teamwork was more on about constant iterations, checking ideas, and saying this paper they claim state of the art, bullshit. Next one. And that's what we. But if you want to merge, majority vote, geometric mean, pick model, like, you know, you do it per class. Let's say my classes work better, like for first 3 classes, my models are better, for other his are better, just pick one, so things like this. Yeah? Next question.
I know you learned a lot from the Kaggle competition, but can you talk about from the sponsor point of view, what do you think they have got out of it?
Okay, about sponsors. So how does it happen like when you get money? So you do this competition, they provide this data, and people that never tried competition, they may assume that sponsors get the solution, deploy them to production, and they have it. No, it doesn't happen in real life. I mean, it may happen, I can't exclude this, but typically it's not the case. Problem with this, these solutions are complex and slow, but it's also part of the deal. There is no guarantee that company organizes this competition that have data scientists that have that skilled enough to be able to understand what's happening. It also depends on the companies, but still, it was the case, guys told me, for a few competitions, and for example, when we gave presentation to the organizers, quality of their questions was significantly lower than quality of the questions that you guys asked today. So, I mean, I'm not even sure that they tried to reproduce our solution. So in this sense, from sponsor point of view, you may think about this PR. Second, of course, they got like, what they got. I mean, they know how much, so if people working for 3 months from like all this number of teams from different backgrounds, they were able to get this accuracy, it's very unlikely that the inside team or something else will get something like 10 times better. So in this sense, you may use these results as a benchmark. But I mean, typically it's just PR. And of course, like, I mean, even their data side is something you just can read through the forum discussions. People share what they did, what worked, what didn't work. It's also an enormous amount of information, especially what looked like a promising idea but didn't work at all. And also people share this appearance of Kaggle scripts, actual code, like simplified solution, non-accurate solution, and get an idea of this. Even at work, typically when I look for some, like I Google some questions that can be stuck or fall, but often I do end up at some Kaggle kernel in which people share some approach that like fits in whatever they work. Yeah. Okay, the question is like, what type of tools and libraries do you use for deep learning and machine learning in general? Okay, my main language is Python for this. In terms of libraries, this is a good question. I use whatever works on me because, I mean, people tend to ask, what is your favorite machine learning library? This is a wrong question. What library works the best for this type of the task with this given set of the constraints? This is correct. Because it can be scikit-learn for deep learning, I use TensorFlow, Keras, I use MXNet for recent program. And in program, I use PyTorch for the next program. Libraries, NumPy, SciPy, all this like Zool. It's pretty hard to say. Basically, what I'm trying to say, I can tell you what exactly did I use for this program, but it's not necessarily the same that it's my common task, common libraries or things like this. What do you mean, like for deep learning? So for this program, I used Keras with TensorFlow backend, I believe. There was another competition that like started after this. I used MXNet for it. Next task, who knows? I'll check different one, try which one I like more, maybe documentation better. Maybe there will be some other guys that work on the same program and they use, let's say, PyTorch. And it will be just easy to discuss questions, issues, loss functions, how to implement this. This is also a big factor. But I just don't stick to any particular, I stick to particular language in Python, but I don't stick to any particular library, whatever works the best. I never used H2O, but I mean, it's my flaw because like guys did great results with this, and they do something on the high level. but I just didn't have the time to invest into this and figure this out. Yeah? Question?
When you were showing the slide with your network on it, you mentioned using an autoencoder.
You see, yeah, so there's like a thing named autoencoder. So let's say you have some images, yeah? And you want to find some representation of them that is like smaller. Yeah? You can try to do it in this way. You can take some image on the left and then collapse it using some kind of max pooling and convolutional layers. And then you just can try to expand this and get back to the original size. And when you train this network, you take as an input and an output exactly the same. But in the middle of the network, there's some bottleneck, and it allows you to do some kind of compression of the image. Yeah? And this is named autoencoder. Segmentation models, they work, all the segmentation networks, they work in a similar regime. Because I mean, when you want to go on some high reach features that like satellite images to something that's much less rich, like masks, you want to lose some information, and then you try to recover it, but in some low resolution way. Yeah? In this sense, if you think of this network, left side looks like a decoder, and right side is an encoder. Yeah? In this sense, yeah, this network is kind of autoencoder type architecture.
So where is the place?
What do you mean?
So the top layer.
So top layer. So what is this like numbers above this like blue?
32 feeding 32. Isn't that the autoencoder where you're reducing the dimensionality of the image?
You see, okay, let's say at the top, yeah, you have like, 32 their numbers. It's like number of filters in each layers. So there on the top, I mean, you feed 112 by 112. Right. Yes, and you feed this, let's say your first convolutional layer has like 32 filters there. And then 3 by 3. 3 by 3. I mean, like convolutional middle is like 3 by 3. But each I mean, you can use 9 by 9, but like in recent years, people tend to go from 9, like let's say, instead of 5 by 5, they use consecutive like 3 by 3, which has similar receptive field, but less parameters. And even these days, I've seen some papers in which they like tend to replace 3 by 3 by 3 by 1 plus 1 by 3 and things like this, because less parameters with similar performance. But yeah, there's a lot of networks, and there's some work about wide networks, and they try to work on these. Sure. You can try it, but I mean, will it work better or worse? I don't know. Probably worse, because when you go like 9 by 9, or maybe better because you see receptive field is bigger, but it can be worse because you're not losing information fast enough. I don't know.
9 by 9 is like edge detection, like some shape, but that's
Typically these days, if you look at VGG16, VG19, everyone is using 3 by 3. If you look at ResNet, I mean, there is 3 by 3, like the most of it, and somewhere close to the top, probably something bigger. I don't remember.
I'm familiar with layering of TNLs, and so, and I've looked at that for say this, but how is, I can understand 32, 32, and then
I mean, so, okay, forget about yellow lines. This is just like skip connections, like influenced by the ResNet architecture. Blue, so you have images that enter at the like left. Then you say you have some convolutional layer that has this like 3 by 3 that's sliding, yeah? And you apply this 3 by 3 to each of this something, you get one layer, yeah? You repeat this 32 times, you have like 32 different filters. That's how you get the first one. Yes. Repeat again, you get another 32. Then if you look, so this network is written in such a way, you need like to look at this as like U form. So from the 32, the same, but with like 64, 128, 256, and then like that. Because it's like, yeah, it's max pooling. So this like, so yeah, this like red arrow is max pooling, in which you're just like picking maximum value within some window of some size. And this means if you can see even visually, we try to make it like this 32, like on the top, they're thin but big. And when you go lower, it becomes thicker, but they're like shorter in terms of like size.
So you guys experimented
close to it. I mean, this architecture of this type is well known to work well for segmentation problem. We optimized it in a way that we created batch normalization, replaced like activation function, probably like played with like filter size and played with input size, but it's not like
that's the one you mentioned.
So yeah, and you see in the senses you go bottom and then top, and kind of U shape, and that's it. Yeah. Question?
I still didn't see where the 10 classes coming out of this filter.
You do it, so of course, like, I mean, you can just predict these 10 classes at the end all at the same time. You just predict some like sandwich that has 10 layers, and each of them correspond to like separate class.
You have to apply a softmax at the end.
Not softmax, as I said, for this class, for this programming class, you are not mutually exclusive. Typically it's softmax, but here it's sigma. Yeah.
I was answering this question. Is the weighted doesn't show the one layer in the classifier?
So yeah.
Every class you said has a different.
This is true. So you can apply it and train one network to bring all classes exactly the same. And as I've said, we're getting to the top 10% of this. But if you like just train separate network for each class, where output is not like 10 layer sandwich, but only one layer, and you train like separate like networks, you get better results. But architecture-wise, the only difference is last layer. Do you predict 1 or do you predict 10?
What's the shaded or hatched?
So hatched and shaded boxes. So as you can see, it's not just like, you know, you go like bottom and then you go up. There's some this like yellow lines. What's happening there? So this is skip connections. And so the skip connections mean that, for example, like at the bottom when you have this like shaded region to 56, it means that you take from the left values of what you get there and concatenate exactly the same values to this like 128 region. So in the sense, information from this 256 to this 128 comes in 2 different ways, directly and also through this bottom part. So just 2 different paths for information to get there. And through the bottom part, there is like some decoding, some exporting, and you use it to extract that information there. And second one, this yellow way, like for sharpening the mask, because otherwise you would not be able to do the predictions on pixel level with the shift pixels here and there. So yeah, yellow like lines for sharpening, and this like main structure for actual information. Yeah.
Do we have a slide on your website? Do we have it posted on the...
Okay, we wrote a blog post that follows this presentation. Maybe more details, more words, slightly different point of view, and this is already published at the Kaggle blog. No free hunch. You can like go to this no free hunch, and there is like our solution, this network, more like description and things like this. Everything is already online. And probably I already published link to it and the comments to this meetup. Do you mind?
So did you use this? Did you share weights or use the training network completely independent?
So we train the network completely independent. The question is, you see, when we train the separate network per class, even when we train per class, you may assume that low-level feature that you extract from the data, they're kind of similar. It may be the case, and we had an idea to train, let's say, for crops and trees one network because they're kind of similar in nature, like vegetation, the classes, the areas, and let's say like roads and buildings, like to have another like network. It's one way. Or you can still train separate networks and use like, you know, low-level features from them. I had this idea, but it wasn't that obvious it will give us anything. That's why we didn't check. So yeah, but yeah.
Probably not might be a good idea for production usage.
For production, just like, you know, like about for production and like sharing weights, I tried to use weights from VGG16 and train this and just initialize bottom part of the network with these weights and like apply it to RGB. Didn't work. I mean, it showed the same performance as like you would as we got here, but yeah, we checked it. Okay.
Do you know of processes that monitor the alteration and adjustment of your approaches for the purpose of reinforcement learning or improving?
I mean, about reinforcement learning, I don't see how directly to use it here. There was some work, one person, like, you know, also in this Russian community, he tries to use guns for this. Basically has separate outputs. He had like some prediction of the mask and also some another output that basically evaluated how good it is. I mean, he got some results, and it's not really reinforcement learning, but still, I don't see how to use reinforcement learning for this task.
No, I didn't make myself clear. I was meaning a self-conscious monitoring of the choices that you're making for this particular data set and how much accuracy is gained by different adjustments or methods that you could do.
No, we didn't. It's like, I mean, as I understand, your question is that we try different approaches, different methods, and you can think, you can measure how different tweaks and different modifications affect your total network performance, yeah?
That's right, and if you accumulate that through time, like with a
I mean, I understand this idea theoretically, but in practice it doesn't really work. First of all, because it's not really the mapping between your changes and your accuracy is not that direct. Like there's a lot of steps in this. And second, you don't have enough of these changes to create some kind of smooth function and like do something about this. And more important, you don't have time for this. For sure, when I was working with models, yeah, I do some submission, some modifications, I do commit, I explained what I was doing for this like particular change, but I mean, I didn't try to extract any information from this like evolution of my ideas to improve this performance. I mean, it doesn't look practical in some sense.
So, is it Macintosh hardware or is it Windows?
I mean, of course, I didn't use Macintosh because there's no GPUs that you can use in Macintosh out of the box, to my knowledge. And I didn't use Windows. I mean, you can use Windows for this program, and some people do it. But why should I use Windows for deployment?
It was Intel, you used an Intel box with Linux and GPUs. That's what.
Yeah, that's what I was doing. I used Linux, yeah. But some participants use like, Sergey, I believe he used Windows. I mean, it's a strange decision. Why would I use it? But yeah, it's possible.
Maybe my hardware for deployment, so I was curious what is the. Because I think I hate Windows and
I mean, I don't know, clearly, I mean, whatever works for you the best, I prefer Linux, and I don't like Mac.
you don't like that? I love that.
But it's like religious holy wars, okay, like back, like any questions about it, right? Yeah.
So when you were training this network as an autoencoder, you had the same image as
No. As I said, like this autoencoder, it's like way, it's network architecture that influenced this. Here, of course, we didn't do it. We have in our train set, we have satellite images, and we had corresponding masks.
Oh.
So we're training like image mask, check what you predict. So we directly train. It's named mask. So when you have some image in which, so basically the thing that you see on the right, which kind of cartoonish size, like satellite, but what you need to predict, it's named mask. Yeah, it's named mask. Okay. No more questions, I believe. Thank you.
You guys ever done one of these conferences? I have a theory that you take and decided to switch to data science.
I don't remember some deep learning, some machine learning. It was long ago, and they're not that useful. They're extremely introductory, and they help you to get some structure to do first steps. But earlier you will start working on some side projects or at work or competitions better.
So you think that you actually learn through the competitions?
Of course, I mean, you learn through the competitions, then X with respect to work or like what you do in academia. That's the point.
So I have a question.
So, and that is that I've focused on line spatial real-time experience. And